Okay, everybody, welcome back. Um, just a quick note. I think today I'm just going to knock out this one chapter. I kind of woke up in some kind of a bug, not 100%, but I think we're just knock out this one chapter. We're quite ahead of our chapters, so we're doing okay. All right. Any questions up to now? Well, let us start with let me start from the beginning. I was going through the checking for stuff here. Okay, here we go. Chapter 7. This is what we're talking about here is chemical bonding. Okay. And now here's the interesting aspect about chemical bonding in chemistry. You would think with all the chemicals out there in the world that there'd be multiple types of chemical bonding, but there isn't. There's only two types of chemical bonding. Okay. And the first type is made up of a combination. Remember, by definition, a compound is made up of one or more, two or more different elements. So the first example of the chemical bonding is made up of a metal and a nonmetal. Okay, that's why it's important that we learn on the periodic table which ones are metals and which ones are nonmetals. An example of this would be like sodium chloride, good old-fashioned table salt. Okay, here we have sodium, the metal, and the chloride, the nonmetal. Now, this type of bond is called ionic bond. The aspect about an ionic bond is that they each have the two species involved in making an ionic bond has a full charge, a full positive, a full negative charge. And they're attracted to each other because of the differences in charge, okay? Just like two magnets coming together. Now, they do not share any type of electrons. Remember, electrons are the ones that create bonds. The ionic compounds or the ionic bonds do not share bonds, okay? They have what we call an electrostatic attraction. They come together because of the respective negative and positive charge, okay? Now, with respect to the other type, that consists of a nonmetal, Nm, bonded to a nonmetal. Now, that type of bond is called a covalent bond. Okay. And a good example of this one would be water. Okay, we have two nonmetals, hydrogen's nonmetal, oxygen's a nonmetal. And we create here a covalent bond. Or another name they give it is molecular bond. Now, the aspect about this is that there is an actual sharing of electrons. And you'll see me draw the structure here and I would say oxygen. Then I draw a line and I connect it to hydrogen. And then the other side, I do the same thing and connect to the hydrogen. Wow. In this line represents two electrons. That bond is a single bond, we call single bond. We got double and triple bonds, but more on that here in a bit. So there are two electrons in that bond. And those electrons are being shared by both the oxygen and the hydrogen, okay? Now, in this particular case, the sharing is not equal. It's not equal sharing because the oxygen is a lot more electronegative. Remember that property we talked about, the electronegativity? Is a measure of an atom's affinity for electrons while it's bonded. Now, in this particular case, oxygen is a lot more electronegative than hydrogen, okay? Therefore, it tends to pull the electrons toward itself, much greater than the hydrogen. Unlike, let's say, hydrogen gas, that I can draw as follows. I've got two hydrogen atoms and then draw a line between them to show the bond. Note that here I got hydrogen on the left, hydrogen on the right. They're equal, the same element. So that bond is being shared equally between the two atoms. Okay, there isn't a pull. There isn't what we call a dipole. Dipole meaning two poles. Okay, we have a lot more to say about dipoles here in a bit. Okay, so two types of bonds, covalent and ionic bonds. Covalent bonds are made up of nonmetal bonded to nonmetal. Ionic bonds are made up with metal and nonmetal. Okay. Now, we're going to utilize the shapes table, and let me show you what the shapes table is. If you haven't printed it out, do so. You will be using it. Okay, so here's the shapes table. And we have a bunch of information on top. Okay, but in the table itself, the shapes itself, we have four columns. The first column is called the general formula. Okay, and from the general formula, there's been assigned a molecular geometry. You know, so what does that bond look like? What does that molecule look like from the general formula? And it also has a name. Okay, that name for an AB2 general formula compound, it has a bond angle 180 degrees between B, okay, is linear. Okay. Now we also have things like AB3. AB3, we have a central atom, and then the three B's are bonded to the central atom. Here's the thing to remember. In creating formulas here and structures, there's always going to be one element that's the central atom, and you always know what that one central atom is. Once you identify the central atom, that tells you that everything else in that formula is bonded to the central atom. Okay? Like here we have AB3. A is the central atom. And B, the three B's are bonded to the central atom. Okay? This particular one has a shape of trigonoplanar. And then we have one here called AB4. It's probably the most common geometry configuration of molecules. We call it tetrahedron. Okay, there's four species here. You got the central atom of A, and then it's bonded to four B's. Okay, and remember that these bonds represented by these lines are made up of electrons. And being electrons, there's two electrons in that bond, they want to repel and stay away as much as possible from another bond. So they're going to spread out and put themselves in a configuration such that it has maximized the repulsion of the electrons. Okay, and when you have four bonds, the maximum repulsion, if you will, is this tetrahedral. Okay. All right, and so on and so forth. Now, we also have some examples of what we call a general formula A, B, E. A represents the central atom. We're always going to have one A, and that's the central atom. You're going to know what the central atom is because what I'm going to tell you, or it will be underscored or written in bold, okay? Which means that whatever else follows, those are not the central atom, and they're bonded to the central atom. All right. So A is the central atom, B is whatever is bonded to the central atom, and that number can vary, as you can see in these examples. And then E represents, this E right here, represents what we call lone pairs of electron, lone pair. Denoted here by these two dots. okay? There are examples of compounds that have structurally in the central atom lone pairs of electrons. And when you see that, it's going to give you a lot more information. We'll talk a little bit more about that in a bit. And we can have either one lone pair in the central, or we could have two. Okay. A good example of the AB2E2 is water. Water is a classic example of an AB2E2. Hold on, somebody's trying to come in. All right. Notice there's two lone pairs on there. And that's just to show the little circle there, like elongated thing, just to show you, it's in an orbital. Okay. And keeping in mind that they're negative charge. Okay. And being negative charged, electrons are going to repel from each other. Well, these lone pairs are going to repel quite a bit. Okay. Because they're negative. The result is this bond angle between, in this case, the two B's is going to be squished and be much, much less from the standard bond angle of 109.5, which is the tetrahedral. That's generally our reference point. And then when you start putting lone pairs in there, that bond angle tends to change quite a bit. As you can see here. So this one here changes quite a bit because that lone pair takes up a lot of space, squishing that bond angle of the AB2. Okay, so we're going to learn how to do this to give us a geometry, then to give us the name of that shape, and then to tell us something about the bond angles. So yeah, do print that out along with the periodic table because we'll be using it quite a bit. All right, we talked about this, that atoms want to they want Nobel configurations, okay? Electronic configurations, meaning that their outermost shell is full with that magical 8 number, 8 electrons surrounding the outermost shell. And atoms do this by either losing or gaining electrons. We know now, I mentioned it, that metals lose electrons. Okay, they lose electrons, whereas nonmetals gain electrons. Okay, the goal is to get the octet, except for helium. Okay, now here's something to remember. See the hydrogen there? Hydrogen will always only have one bond. Like, for example, we did earlier with water. I had water, H, and then I had a line and then hydrogen. Okay. And then the other side, this is the structure for water. Okay. Now, hydrogen, because it's duet law or rule, can have at the maximum only one bond. Okay, that's it. One bond. Okay, now water again has 2 lone pairs. And let me talk about how they share in these electrons. For example, the bond right here is 2 electrons. It is shared with hydrogen and it is shared with oxygen. So it counts to both of the atoms. So there's 2 electrons to hydrogen and 2 go to oxygen. The same is true on the other side. 2 electrons on the other side that are shared with the hydrogen and the oxygen. So what we have is, well, first of all, the duet has been fulfilled for hydrogen, okay, just one bond. The octet is fulfilled for oxygen. Count the number of electrons around oxygen. They had the 4 lone pair, here, which are the two dots. It's 4 electrons there. And then each line represents 2 electrons. So I got 4 electrons. So 4, 4 plus 4 is 8. So there are 8 electrons around oxygen. 2 of them are lone pair, and the other 2 are being shared with hydrogen in the compound. Okay. So when we start counting the octet for a bond, that electron counts to both in the direction of the atoms that are bonded together. Okay, because they're sharing it. They're sharing that bond, those electrons. Okay, now metals lose electrons and become cations, and nonmetals gain electrons and become anions. Okay, now when you get a combination of a metal and a nonmetal, as I mentioned in the beginning, we have what is called an ionic compound, ionic bond. Okay, they have a full-fledged positive charge and negative charge. And therefore they are attracted to each other electrostatically. They just come together, like 2 magnets. There's no sharing whatsoever of those electrons. Okay. Now, when we start putting compounds together, you got to remember what you want to put together is the positive ion and the negative ion. It won't work to put 2 positives together, okay? Or 2 negatives together. Why? Because they repel each other, okay? Positives and negatives repel each other. But a positive and a negative attract each other. So you're always going to have, for ionic compounds, you're going to have a metal, which is going to always lose electrons, resulting in a positive charge, and a nonmetal, which is gaining electrons, which has a negative charge, and hence they come together, okay? So in this case, a good partner for calcium ion would be the bromide, not the lithium. Okay, some examples of ionic compounds, okay? Now notice something here, the way that the formulas are written, okay? You will find that 99% of the time, the metal is written first in the formula. So you can see here potassium, and then the other one's called calcium, okay? So potassium and then chlorine, well, it's the element, it's a nonmetal, it's going to gain electrons and become a negative charge. It also is going to change its name from chlorine to chloride. So the name of KCl is potassium chloride, okay? The next one is calcium bromide. Now notice the subscript 2 is telling us that there are 2 bromides, okay? With no subscript number, it's assumed to be 1. So I got 1 potassium, 1 chloride. So for every calcium, I need 2 bromides. You might ask, well, why is that? Well, look at the charge of calcium. Calcium has a +2 charge as an ion. It's a group 2 element, metal. And when it loses its electron, it's going to lose those 2 valence electrons. The bromine is in group 7. It's a nonmetal. It's going to pick up an electron because it will have that 8 fulfilled. So it ends up in a negative charge. Okay. Now, when I put these together to write a formula, I have to put enough positives and enough negatives together so they cancel each other out. Right now, I got a +2 and a -1. Obviously, they're not canceling each other out. So I need to add 2 -1s. Okay? 2 -1s for every +2s of calcium. And this 2 here now becomes the subscript for the formula calcium bromide. Okay, with respect to metals, now notice something here when I named it calcium bromide. There's 2 bromides. I did not say calcium dibromide. I just simply said calcium bromide, which brings me to a point. When it comes to ionic compounds, we don't use prefixes like calcium dibromide. It's just simply calcium bromide, okay? We don't use prefixes, unlike covalent compounds where we do, like CO2, carbon dioxide, CO, carbon monoxide. Yeah. So for covalent compounds, yes, we do use prefixes. And for ionic compounds, no prefixes. Okay, remember that part. All right, with respect to covalent compounds, we have a nonmetal bonded with each other where they're sharing electrons. So it's a nonmetal combination. They're sharing electrons, which could be either equal sharing because the electronegativity of the two elements are the same, okay? Or it could be unequal sharing because the electronegativity of the elements is different. So one element is going to be hugging all the electrons, if you will. Okay, all of the diatomic elements are covalent compounds. So have no fear of ice cold beverage. All diatomic, all of them covalent compounds. Okay, and some other examples there, we have water and carbon dioxide, and carbon monoxide. Any combination of nonmetals represents a covalent compound. And any combination of metal and nonmetals represents an ionic compound. Okay, so we're going to start working on writing ionic formulas. Now, when we're writing formulas, it can be two things can happen. You could be given a formula and asked to write the name, or vice versa. Having the name, you need to write the formula. Okay, so in this scenario here, it's asking you, why is the formula CaBr2? Why 1 potassium for 2 bromides? What do you guys think? Yeah, here's the formula. Why are there 2 bromides for every calcium? Any ideas?
Calcium lost one? No?
What? Okay, not quite. In fact, I went through this example. What is, when calcium becomes an ion, what is calcium's charge? Okay, what group is calcium? Positive what? 1, 2, 3?
I believe
You broke up.
1.
I hear
Is it
1. No. What group is calcium in?
Oh, wait, I think it's 2.
You got it.
Yeah.
So calcium is a +2 ion, okay? It becomes a +2 because it lost 2 electrons. It lost those 2 valence electrons. Now, the bromide, what kind of charge does the bromide have? Find it on the periodic table and find out what group it's on.
It's in group.
It's in group 7. Yeah, Erica, you got it correct.
It's in group 7, yes.
Right. So when it becomes an ion, what is its new charge now? Because it picked up 1 electron, right? Because it's in group 7. So now bromide has a -1 charge. Okay?
Yes.
All right. Now I want to put these 2 together. But remember, I want to put them together such that the charges equal 0. So that means that I need 2 bromides for every 1 calcium. Does that make sense? Because I want them to equal 0. If I had aluminum, which is a +3, and I have bromides, how many bromides do I need for aluminum bromide? You need three, exactly, Catherine. You need three of them, okay? That means that the formula for aluminum bromide would be AlBr subscript 3, okay? Make sure it's a subscript. Okay, that represents, the subscript represents how many atoms of bromide. Calcium would be CaBr subscript 2, calcium bromide. Okay, notice the naming too, aluminum bromide. We didn't say aluminum tribromide. Okay, we just said aluminum bromide, flat out straight, okay? If it was an ionic compound, then yeah, we can use prefixes to name them, but it's covalent compound, but it's not the case. These are ionic compounds. All right, so the point of ionic compounds is when we put them together, we want to put enough positives and enough negatives together so they cancel each other out, okay? And that number that I need to cancel the negatives, that's the subscript of the anion. Right. And this is why calcium is a +2 and the bromides are a -1. So it's important that you pick up on the fact that they're on the, where are these elements? And we're going to be working mostly with group 1 and 2 metals and the non-metals, okay? We will get into the other ones, the transition metals in there with gold and the other ones, but at a later date. But the goal here is to put enough cations with whatever charge they have to add enough anions such that when I put them together, they cancel each other out, okay? And that gives me the formula for that particular compound. I just did aluminum bromide. That could have been aluminum chloride or aluminum iodide. See, you can start building the database. So, you know, I said bromide, but you could have used any of the halides. Okay, now, yeah, this is, now, this is a question that's popped up, and I can understand where you know, a student may think, okay, it's diatomic. So I write the formula as CaBr2, okay? And they may think that, you know, they know that bromine, you know that bromine is diatomic, okay? Diatomic, bromine itself. And this will suggest, hey, maybe I'm looking at diatomic bromine here, but you're not, okay? Because what you're looking at, the very first item that's bonded to the BRs is a metal, in this case calcium. If it was the bromide all by itself sitting there with no other metal, yes, then there's bromide. Okay, so this is not diatomic bromide. Not diatomic bromide. Or in this case, bromine, I shouldn't say bromide. All right, question here is asking you which compounds are ionic? What's the criteria to be ionic?
Metal to non-metal?
Metal to non-metal, that is correct, okay? So we look at the first one. We got KBr, which what do you think you guys, the name of KBr is? If you had to name it.
Potassium bromide?
You got it, potassium bromide. Do you think that's ionic?
Yes.
Yes, it is. So definitely potassium bromide is ionic because we have a combination of a metal and a non-metal. How about this one? Sulfur and 3 oxygens. What do you think? Ionic?
Covalent?
Covalent, exactly. And notice something about the name here. We would name this sulfur trioxide. Smelly gas. In fact, a lot of vehicles have that in the exhaust. And okay, HCl, ionic or covalent?
Covalent? No?
Yes, it
Covalent?
is. Yep, definitely covalent. So we have covalent here. I'm just going to label C, I for potassium bromide for ionic. And then we got Br2, which is bromine. What do you think? Ionic or covalent?
Covalent?
Yeah, another covalent. And then we have carbon dioxide. Notice again, covalent, but we use prefixes like we did sulfur trioxide. We also, if it would have been sulfur dioxide, that's a prefix we use, but only for covalent compounds, we use prefixes. And okay, so we have covalent for carbon dioxide. And what about the last one? What would you
Ionic?
call ionic? What would you call it name-wise if you had to name it?
Magnesium chlorate?
No. Not the eight, not the eight or the IDE.
Chloride.
Chloride, yes. Okay, we're going to talk about the 8 and the I at a later date. Okay, but right now, when we're dealing with the non-metal all by itself, okay, then it's an IDE. Okay, no, not dichloride, Catherine. Dichloride, the prefixes are only reserved for the covalent compounds. Okay, so magnesium chloride, we just simply magnesium chloride, even though it's got 2 of them. Okay. All right, so let's clear this up here. So the only 2 that are ionic are the potassium bromide and the magnesium chloride. All right, now let's talk about electrons and the transfer of electrons when we are creating ionic bonds. Okay. Now you have a sodium atom here, represented by, I guess, red color. Okay. Right here. And notice what happens to the diameter when it loses an electron. Sodium has 1 valence electron, okay? And it loses that 1 valence electron to give you a sodium plus ion. And the result is that 1 valence electron, which was out was in the valence shell, now is empty. So the new radius shrinks, it's smaller, next level in, okay? So you can see the difference in diameter with respect to the sodium atom versus the sodium ion. The opposite is true when you're dealing with the anion. Okay, you have the chloride, the chlorine atom, okay? It picks up an electron because it has room for 1 more, and its diameter gets bigger, its radius gets bigger because that electron is now in the outermost shell. You got the octet fulfilled. And, 8 electrons are going to repel each other quite a bit. And so you had the new radius is bigger for the chloride ion than it is for the chlorine atom, okay? Notice how they bond with each other. Right here, it's just an attraction. There's no sharing whatsoever of electrons. It's like 2 magnets coming together. That is ionic bonding, okay? Now, the aspect about ionic bonding that is true for every ionic compound is even the ones we're going to learn about solubility, even the ones that are labeled as insoluble, even those have a little bit that goes into solution. There's nothing out there that can say it's totally insoluble, okay? But the point is that when ions like this sodium chloride in the solid phase go in solution, they break apart to form their respective ions in the solution. Okay. And when they break apart to form these ions, they can now conduct electricity. Our next experiment, which is Wednesday, we're going to deal with conductivity. We're going to look at different solutions that have ions and then see if they conduct electricity. Okay. And they will conduct electricity if it's ionic. Now, some of them will conduct very strongly, and some of them will conduct very weakly. It depends on the solubility of the compound. All right. Now, let's consider the magnesium and the sulfur atoms, and then we're going to look at the ions, okay? So we have the magnesium atom at 12 protons and 12 electrons, whereas the ion, which has a +2 charge, and we know it has a +2 charge because it's in group 2A. 2A tells you there's 2 valence electrons, and it's a metal, so it's going to lose those 2 valence electrons. Plus, we end up with a +2 charge for the ion. So now it has still has 12 protons, but now it has 10 electrons. Sulfur starts off with 16 protons and 16 electrons as the element. It is a nonmetal. Okay, it's going to pick up 2 electrons because it is in group 6. So it needs 2 electrons. It's in group 6A. It needs 2 electrons to get that octet fulfilled. All right, so now it has 16 protons and 18 electrons. Okay. Now, what we do here to write a formula, once you put them in an ionic form, now I can now calculate how many of each I need. So you notice that the magnesium ion is a +2, and the sulfur, which is now called sulfide, is a -2. So I can write the formula simply as MgS. Okay, because the +2 and the -2 cancel each other out, so I just need one of each. And the name is magnesium sulfide. Okay, sulfide. It went from sulfur to sulfide. Oxygen goes from oxygen to oxide. Phosphorus goes to phosphide. Okay, IDE. All the halogens go to halide, so it'd be chloride, bromide, etc. All right. All right, so just to recap on ionic size, cations have lost electrons, so there are more protons. So they pull the orbits that they had left a little bit closer, and they result in being smaller, okay, because there's more protons than there are electrons. And the anions gain electrons, there's more electrons, and they repel and push orbits further apart because of the repulsion aspect of the electron. So they have a larger diameter, okay? So what we can say is the following true or false? It says the aluminum atom loses electrons and the iodine atom gains electrons. What do you guys think?
True?
True, yeah, exactly. Because aluminum is a metal, so it will lose electrons. And iodine is a nonmetal, so it will gain electrons. Okay. Now, the aluminum atom, read it carefully, the aluminum atom is larger in radius than the aluminum ion. What do you think?
false.
False, you sure?
No.
Refresh your memory on where do you go? Right here. Look what happened to the sodium.
Oh, yeah.
Yeah, see how when they lost electrons, it got smaller. And the anion gain electrons, it got bigger. Okay. And so,
Okay. Okay.
all right, so here that's a true statement. The aluminum atom is larger in radius than the aluminum ion, because the aluminum ion comes
I was
about.
thinking the opposite.
Yes, exactly. All right, the iodine atom is smaller in radius than the iodide ion. That's a true statement. There you go, Erica. Okay, because the opposite for the anion, because the anion pick up electrons, and now you have a lot more repulsion because of the extra electrons in there. Got a little more crowded in there, so the radius gets a little bit bigger. Okay, and the aluminum and the iodine ions form a bond by attraction, and that is true because we have a full-fledged negative charge and a full-fledged positive charge. Specifically, if we were to draw the formula, because aluminum has a +3 charge, and the iodines have a -1 charge, right? Just like the bromide and the chloride. I need 3 iodines for every aluminum +3. So the formula is Ali subscript 3. Aluminum iodide. Not triiodide, but just simply aluminum iodide. And when they come together, because they have a full-fledged charge, negative charge, even though I'm not showing it here, where'd it go? Even though I'm not showing it here, I'm showing it neutral charge because I put enough positives and enough negatives to cancel each other out. Okay, but in solution, they will break apart into their respective ions and conduct electricity. All right, covalent compounds. There are, with respect to covalent compounds, I did write an example of water, and I drew a line, and that represented a single bond. Okay, so if I have a species of A bonded to A, that represents a single bond, one line. And there's 2 electrons in that single bond. I can also have a scenario where I got 2 lines. That represents a double bond. Okay, there are 4 electrons in that double bond. And then our last example is a triple bond, where I have 3 lines here. Each line represents 2 electrons, so I have a total of 6 shared electrons in that triple bond. And that's it. That's all the bond types that we have for covalent compounds: single, double, or triple. Okay. And remember that because we're going to need that information. All right, so here's a model of carbon dioxide, where you have carbon in the dark here, and the red is represented by oxygen. And then you have H2O, or water. Okay, the red sphere is represented by oxygen. And the white ones are hydrogen. Okay. All right, so like I stated, single bonds are 2 electrons, 1 pair, they're being shared. Double bonds are 4 electrons being shared. And then finally, triple bonds have 6 electrons, being shared. Now, the single bonds are the longest and the weakest. And then we have the triple bonds that have the shortest and the strongest. In fact, they have a lot of energy built up. You know, a acetylene torch is enough energy. It's a acetylene and oxygen in a torch that you can get it hot enough to burn metal. Okay, so it's a lot of energy. You can't really do that with, say, butane, which is all single bonds. Okay. Now, excuse me. It was thought that when these compounds came together to make a bond, that when they came together, they just would, the radius they had would just be the sum of the radius that each individual atom would have. Okay, for example, let me explain here. We have the hydrogen atom, which has a radius of 0.037 nanometers, very tiny. We have the chlorine atom that has a radius of 0.99 nanometers. It was believed that when they make a bond, that the radius of each atom would just simply combine so that the new radius would be just the sum of the radius 1 and 2, which would be 0.136 nanometers. Okay, reasonable guess. But then it turns out that's not the case. That when you did a bond analysis, the new bond angle was actually, not angle, but bond length was actually 0.127 nanometers. Okay, big difference from 0.136. And so the question was, well, what's going on here? Well, what's happening is there's an area right in here that some of the hydrogen contribution and some of the chlorine's contribution get together and they share that area. They actually make a mesh, if you will, because they're sharing that electron. And their total bond length is much less than the sum of each individual bond length. Okay. Right. Now think about bond energy. Energy is going to be required to either bond or to break or form a bond. And breaking bonds always requires energy. Always requires energy. So when we do is we treat energy as a reactant and it is absorbed. In fact, it gets cold. That particular process is called endothermic. That's a cold process. If you go to the, like CVS pharmacy and buy yourself a cold pack, you get the pack and you smash it, that thing gets cold. That's an endothermic process. Okay. And so here you have HCl plus heat / energy. It's as a reactant because it's breaking the bonds and it generates the hydrogen atom and the chloride atom. Okay. When we form bonds, it releases energy. And we call that exothermic. So it gets warm. And a good example here too, and not only is a cold pack, but there are hot packs you can buy. They have the chemicals that you smash and it gets warm. Okay, it's an exothermic process, gives off heat. Okay, so in this case, energy is a product. It is produced. So here, just the opposite reaction we just did, where you got the hydrogen atom and the chloride atom combined to form HCl, and then energy is given off. Okay, true or false regarding H2S, which dihydrogen sulfide is the name for this one. Electrons are shared in H2S. What do you think?
Yes.
Yes, they are, because they are covalent compounds. True. All right. The bond between the hydrogen and the sulfur is ionic. What do you think?
False.
It definitely false, because you have hydrogen and sulfur are nonmetals. Remember, on the periodic table, you have hydrogen on the far left. And you might think that it is a metal, but it's not. Okay, let me pull up mine. Right here, hydrogen's over here on the far left. And it happens to be there with the other metals. And you might think, yeah, it's a metal, but it's not a metal. Remember, hydrogen's a non-metal. Okay, so far so good. All right, the HS bond length is less than the sum of the two atomic radii. The bond length between hydrogen and sulfur is less than the sum of the two atomic radii.
True.
That is true, okay, because there's that overlap that occurs in this covalent bond. And then breaking the HS bond releases energy, and that'd be false, okay? Breaking the bond, forming the bond would be true. All right, which brings us to, let's tell you what, let's take a little break. Let's do 15. I got 223. Call it 238. Call it 240. 240. All right, I'll be back 15 minutes.